PixelGrid, an adaptive distributed image processing pipeline developed for our
This
parallel
was
and
our
distributed
project
computing goals.
PixelGrid
Our
for
project
parallel
focused
and
on
distributed computing.
processing large
Thank you
image
for listening
dataset
to our
efficiently using
project,
multiple machines
and I
working
hope
together.
you liked it. Thank you very much.
The problem: large-scale image processing is slow on single machine. Also, equal task distribution causes fast machine to wait for slower one. So we need a system that is both parallel and adaptive. The solution: PixelGrid uses a master worker architecture. The master distributes images batches while worker processes them in parallel. We used Python 3.9 plus, TCP sockets for communication, multiprocessing for parallelism, OpenCV and Pillow for image processing. Architecture: our system runs on two laptops connected through LAN, local area network. Laptop A hosts master node, load balancer and dashboard, uh, which is and also a worker A. Laptop B hosts worker B. All communication happens through message passing using TCP sockets. Workers and masters communicate using four message types: register, task, heartbeat, and result. This ensures reliable and structured communication across the distributed system. Execution flow. The workflow has 5 stages: task creation, adaptive distribution, parallel processing, aggregation, and live monitoring through dashboard. Parallelism. To bypass Python GIL limitation, we use multiprocessing. Each worker processes images in parallel using multiple CPU cores. The pipeline applies grayscale conversion, edge detection, and histogram equalization. Adaptive load balancing. Instead of sending equal work to all workers, PixelGrid dynamically adjusts batch sizes. Fast workers get larger batches while slow worker gets smaller ones. This maximizes overall system efficiency. Fault tolerance. If a worker fails, tasks are not lost. The master uses an in-flight registry, a 15-second watchdog timer. Failed tasks are automatically reassigned, ensuring 100% task recovery. PDC concepts. PixelGrid demonstrate key PDC concept: task and data parallelism, inter-process communication, master-worker architecture, and Amdahl's law. For 1000 images, sequential processing took about 12 seconds. PixelGrid is completed it in about 6.5 seconds. This achieved nearly 50% reduction in processing time. Scalability. As the number of the worker increased, speed up also increased. Our result closely followed Amdahl's theoretical scalability curve, showing efficient parallelization. PixelGrid also includes a real-time monitoring dashboard. It displays throughput, node status, system activity, all accessible through a web browser. In conclusion, PixelGrid is scalable, adaptive, fault-tolerant. It successfully demonstrates how a distributed system can significantly improve image processing performance using Python.
This is the PixelGrid live dashboard. It updates every 2 seconds in a real time as images are being processed across two laptops. The top card shows the key number, how many images have been processed, our achieved speed up, efficiency, and total runtime. These two node cards shows worker A and worker B live. You can see which one is idle or busy, their average latency, and how the system automatically adjusts their batch sizes to keep both workers balanced. The throughput card shows how many images per second each work processor i- is processing per batch. The latency chart shows how long each batch takes per worker. The most important chart is the speed up curve. The dotted amber line is Amdahl's law, the theoretical maximum speed up possible with two workers, which is 1.93x. The blue line is our actual speed achieved speed up, which is 1.87x. That's 3% gap is explained by socket communication overhead and process spawn time. Exactly what does law predict? And at the bottom, the batch log shows every single batch which were processed it, how fast and whether it succeeded. The entire pipeline task distribution, parallel processing, fault tolerance, and this visualization runs on two personal laptops connected over a phone hotspot. This was our project PixelGrid for parallel and distributed computing. Thank you for listening to our project and I hope you liked it. Thank you very much.